The most famous equation in the world did not arrive with a mushroom cloud. It arrived as a short paper with a boring title. Does the inertia of a body depend upon its energy content? Einstein was 26. He was working in the Swiss patent office. The paper was only a few pages long, and the core argument was almost embarrassingly quiet. Imagine a body floating in space. It emits two identical flashes of light in opposite directions. It does not recoil. Nothing dramatic happens. But when you do the same accounting from a moving train, something refuses to balance unless the body has lost a little bit of mass. That is the whole doorway. Not matter turns into energy as a magic trick. Not a bomb is hidden inside every atom as a slogan. The deeper claim is colder and more powerful. Mass is not a separate thing from energy. Mass is what energy looks like when it is locked inside a system and measured at rest. The conversion rate is the speed of light squared. That square is why a visible amount of energy can come from an invisible amount of missing mass. The equation is tiny, E equals mc squared. But the sentence underneath it rewrote physics. Mass is concentrated energy. Before Einstein, physics kept two ledgers. One ledger was mass, the other was energy. Conservation of mass said matter was not created or destroyed. Conservation of energy said energy could change form, but the totals stayed fixed. At ordinary scale, that split looked perfectly reasonable. Burn coal in a furnace, and the ash and gases weigh almost exactly what the coal and oxygen weighed before. Charge a battery, and it does not become noticeably heavier. Wind a spring, and your scale does not move. So for 19th century instruments, mass seemed conserved on its own, and energy seemed conserved on its own. Then the clean separation started to crack. James Clerk Maxwell's equations showed that light is an electromagnetic wave moving at a fixed speed. Radioactivity, discovered in the 1890s, revealed matter releasing energy in ways chemistry could not explain. Radium salts gave off heat for years. Uranium compounds fogged photographic plates. Something inside the atom seemed to be paying the bill, but nobody had a complete account of what was being spent. That raised a new class of questions. If radiation carries energy, does it also carry inertia, meaning resistance to acceleration? If a hot object contains more energy than a cold object, should it also be slightly harder to push? If a nucleus releases energy, should the products weigh a little less than what you started with? Today, those questions sound natural. At the time, mass and energy were different nouns. And that matters because the original puzzle was not how to build a bomb. That came much later, after nuclear physics, neutron discovery, fission, chain reactions, and wartime engineering. The earlier puzzle was deeper. If the laws of physics are the same for all observers moving at constant speed, and if light always moves at speed c, can mass and energy really remain separate accounts? Einstein's answer was no. A simple analogy helps. Imagine two bank accounts. One is labeled matter, the other is labeled energy. Old physics treated the matter account as sealed. Einstein found the exchange rate between the two. The seal was never real, and the exchange rate was enormous. To see why the formula matters, you have to know what each symbol means. Start with E. E means energy. More specifically, in the clean modern reading, it means rest energy. That is the energy a system has when you measure it in the frame where the system as a whole is not moving. That distinction matters. A moving baseball has kinetic energy, which is energy of motion. A particle in an accelerator has both energy and momentum, where momentum is motion weighted by mass and speed. The famous short equation refers to the energy that remains even when overall motion is zero. Now take m. M means mass, but not amount of stuff in the casual sense. In modern physics, it means rest mass, also called invariant mass. That is, the mass measured in the system's own rest frame. If you heat a sealed box, charge a battery, compress a spring, or store energy in any closed system, that stored energy contributes to the system's mass. Usually, the effect is too small to notice, but it is real. Then there is c. c is the speed of light in vacuum. It is about 300 million meters per second. The equation uses c squared. That is roughly 90 quadrillion in standard units. That huge number is the reason the formula feels almost unreal. It says 1 kilogram of rest mass corresponds to about 9 times 10 to the 16 joules of energy. 1 gram corresponds to about 9 times 10 to the 13 joules. A good way to picture it is as a currency exchange with an absurd rate. Mass is one currency, energy is another. The booth offers so many units of energy for each unit of mass that losing a microscopic amount of mass can release an enormous amount of energy. That does not mean you can easily spend the full balance. It means the price tag is vast. The more practical version of the equation often uses change instead of total amount. Delta E equals delta M times c squared. Delta just means change. If a system loses a tiny amount of mass, the released energy equals that mass change times c squared. If a system absorbs energy and traps it, its mass increases by that energy divided by c squared. So a charged battery is slightly heavier than a discharged one. A hot object is slightly heavier than the same object when cold. A compressed spring is slightly heavier than a relaxed one, and a bound atomic nucleus is lighter than the separate particles that could have made it, because binding energy has already been released. That last case is where the equation becomes visible. In chemistry, the energy differences are so small that the related mass changes are tiny beyond ordinary measurement. In nuclear reactions, the energy differences are much larger for each atom. Then the missing mass becomes measurable. Nothing violates conservation. Conservation just had a hidden account all along. Now the famous equation itself. E equals mc squared. Read plainly, it says the rest energy of a system equals its rest mass times the speed of light squared. The trap is to hear that as if mass and energy are two different substances that swap costumes. A better reading is bookkeeping. Mass is one form in which energy is stored. Energy is the broader, conserved quantity. That is why the change form is often the clearest. Delta E equals delta M times c squared. If a nuclear reaction releases energy, the final products have less rest mass than the starting ingredients. The missing rest mass did not vanish. It came out as other forms of energy. That can include motion, heat, or gamma radiation, which is very high-energy light. Here is the scale. Take 1 gram, which is 1,000th of a kilogram. Multiply by c squared. You get about 9 times 10 to the 13 joules. That is a staggering amount of energy from an amount of mass lighter than a paperclip. But in real reactors and in the sun, only a fraction of the participating mass shows up as released energy. The products still retain almost all of the mass. What matters is the difference between one arrangement and another. That is why the phrase, "convert mass into energy," can mislead. Most of the time, matter does not simply dissolve into pure light. What actually happens is subtler. One arrangement of particles has a different rest mass from another arrangement. The gap is paid out as energy. Think of a nucleus as a tightly built vault. Rearrange the structure, and a small difference in binding energy comes out as heat and radiation. Modern physics places the famous equation inside a larger one. E squared equals open parenthesis p times c, close parenthesis, squared, plus open parenthesis m times c squared, close parenthesis, squared. Here, p means momentum. If the object is at rest, p is 0. Then the relation reduces back to E equals mc squared. So the famous formula is not the whole story. It is the special case for rest. That special case is powerful because it tells you something profound. Even when motion is 0, energy is not 0. A body sitting still carries the energy of its mass. Einstein reached this with a remarkably quiet thought experiment. Imagine a body floating in space. It emits 2 equal pulses of light in opposite directions. Because the pulses are equal and opposite, the body does not recoil. In its own rest frame, the event is perfectly symmetric. The body had some energy before, it has less after. The light carries away an amount of energy, which Einstein called L. Now watch the same event from a frame moving past the body. Because of relativity, the two light pulses are not measured the same way by that moving observer. One is shifted differently from the other. So the total energy carried by the light, as measured in the moving frame, is not simply the same neat amount. Here is the key move. Energy still has to be conserved in both frames, but the body did not change its speed. So if its kinetic energy, meaning its energy of motion, changes while its speed does not, then something about its inertia must have changed. Its resistance to acceleration must be lower after it emits the light. Einstein concluded that if the body emits energy L, its mass decreases by L divided by c squared. Turn that around, and you get L equals delta m times c squared. No nuclear reactor is needed for the argument. No knowledge of the nucleus is required, just relativity, light, and conservation of energy. An everyday analogy makes the intuition clearer. Picture a suitcase on wheels. You cannot see inside it, but you can feel how hard it is to push. Remove heavy contents, and it becomes easier to accelerate. Einstein's point was that energy itself is part of the hidden load. If energy leaves as light, the suitcase becomes slightly easier to push. If energy is added and trapped inside, it becomes slightly harder. Later physics expressed this in more elegant language. Energy and momentum are treated as parts of one relativistic object. Different observers can disagree about how much of a system's energy is due to motion, but they agree on the rest mass. So E equals mc squared is what the energy ledger looks like when you stand still with the object. That changed the basic meaning of mass. Before Einstein, mass was treated mainly as a quantity of matter. After Einstein, mass became a property of energy. But the famous formula hides several traps. The first is that E equals mc squared is not the full moving particle formula. If a particle is moving, total energy also depends on momentum. That is why light can have energy even though a photon has zero rest mass. A photon carries momentum, so it still carries energy. Rest mass is not the only way energy exists in relativity. The second trap is conservation. The equation does not mean energy appears from nowhere. It means mass and energy belong to one conserved ledger. In nuclear fission, the fragments are lighter than the original nucleus and incoming neutron by a small amount. That small mass defect appears as released energy. In fusion, the final helium and other products are slightly lighter than the hydrogen nuclei that went in. Again, the difference appears as energy. The same logic shows up in medicine. In positron emission tomography, called PET, a tracer emits a positron, which is the electron's antimatter partner. When the positron meets an electron, the pair annihilates. Their rest mass appears as two gamma photons moving in nearly opposite directions. The ledger balances exactly. The third trap is practical access. 1 gram of rest mass corresponds to an astonishing amount of energy. But ordinary matter is not a simple battery you can cash out at will. Chemical reactions release tiny energy differences. Nuclear reactions release larger ones. Fusion offers huge energy density, but controlled fusion is a brutal engineering problem. Fission works, but it comes with fuel, waste, safety, and political constraints. The formula gives the exchange rate. It does not give you the machine. The fourth trap is historical. E equals mc squared is often tied directly to the atomic bomb. That link is understandable because nuclear weapons are dramatic demonstrations of mass energy release. But the equation alone did not build them. The bomb required the discovery of fission, neutron physics, isotope separation, reactor work, explosives engineering, industrial capacity, and wartime decisions. The formula revealed the ledger. Human beings chose what to do with it. The fifth trap is that the equation is not only about nuclear reactions. Any stored energy contributes to mass. A hot cup of coffee, a stretched rubber band, a charged battery, a molecule, a spring, all obey the same accounting. We ignore those changes because c squared is so large that ordinary energy divided by c squared gives a tiny mass difference. Nuclear physics is famous only because the same rule becomes measurable there. So the formula is both broader and less magical than the slogan. It governs every system. It powers stars. It underlies reactors. It explains medical imaging. It helps explain why particle colliders can create new particles from kinetic energy. But it never suspends accounting. It is accounting. Now watch what that buys you in the real world. The first payoff is energy density. Nuclear energy is powerful not because atoms are mystical, but because nuclear binding energies are large enough that small mass defects can become useful heat. A fission reactor is not cartoonishly destroying matter. It is rearranging nuclei into configurations with lower rest mass and collecting the difference as heat. That heat boils water, steam turns turbines, electricity reaches the grid. The second payoff is the sun. Hydrogen nuclei fuse into helium through a chain of reactions. The final products weigh slightly less than the starting ingredients. The missing mass becomes energy. It begins in the solar core as radiation and particle motion. It works its way outward and eventually reaches Earth as sunlight. Solar panels, crops, fossil fuels that began as ancient life, and even weather all trace back to this bookkeeping. The third payoff is medicine. PET scanning depends directly on mass-energy conversion. A positron emitted by a tracer meets an electron in the body. Their annihilation produces 2 gamma photons. Detectors catch those paired photons and use them to reconstruct where the tracer was. A physician looking at a tumor's metabolic activity is relying on the same exchange rate Einstein uncovered. The fourth payoff is particle physics. Accelerators pour kinetic energy into particles and smash them together. Some of that collision energy can appear as the rest mass of new particles. That is how heavy, short-lived particles can be created and studied even though they are not part of ordinary matter around us. The collider is a currency exchange machine. Motion energy goes in, new mass energy configurations come out. There is also a practical rule hidden inside the formula. Whenever someone promises a revolutionary energy source, ask 4 questions. What energy transition or mass defect is actually being accessed? What fraction of the theoretical energy is really convertible? What engineering system captures it? And what safety, waste, supply chain, or control problem destroys the economics? E equals mc squared gives you the ceiling. It does not give you a viable business. That is the enduring lesson. Tiny mass differences can support enormous energy flows, but only if the surrounding system can control the reaction, capture the output, and do so at acceptable cost. The formula teaches respect for hidden energy density. It also teaches caution around slogans. It tells you the conversion rate. The real world decides whether that conversion is accessible. Mass is not separate from energy. Mass is locked energy, and c squared is the exchange rate.